You know, for decades now, we've been pointing our biggest and best telescopes out into the cosmos, hunting for new planets. And what we found is, well, it's a cosmic zoo, an absolutely incredible variety of worlds way, way outside our own little solar system. But there's a big mystery at the heart of all the searching. It's a really strange, almost deafening silence, right where we'd expect to find something very, very familiar. So today, we're opening the case file on the hunt for exomoons. First things first, let's get some context here. The search for exoplanets, that's planets orbiting other stars, has been, just wildly successful. Just since 2015, the number of confirmed planets has more than doubled. We are now at over 4,500 confirmed alien worlds. We're talking everything from these scorching hot gas giants to tiny little rocky planets, some even smaller than our own moon. It's a staggering number, really. And yet, here is the number of confirmed moons orbiting any of those planets. 0. A big, fat 0. Not a single one has been definitively 100% proven to exist. Now, think about our own solar system. It is absolutely teeming with moons. So this is a massive cosmic puzzle. And yeah, this is the central question. This is the one that keeps astronomers up at night. You have to wonder, right? Is our solar system just some kind of weirdo anomaly? Are moons actually incredibly rare in the universe? Or are we just not looking in the right way? This is the mystery we're going to try and unravel today. So let's do this right. Let's treat this like a cosmic detective story. First, we're going to dig into the mystery itself, all the tantalizing clues and near misses we've had so far. Then we'll open up the Exomoon Hunter's toolkit and look at the forensic methods they're using to spot these hidden worlds. We'll also see why it's so darn hard to crack this cosmic code, explore the motive, because you always need a motive, why this search matters so much, and finally, we'll see where the hunt is headed next. All right, let's get into it. Part 1. And like any good mystery, this one is just full of these intriguing leads that end up being frustrating dead ends. It's not for a lack of trying either. We've had several really promising candidates over the years. See, the problem is that the signals we're searching for are unbelievably faint. That makes it super hard to tell them apart from, just noise from the telescope or some other cosmic event. A perfect example of this is the candidate moon around the planet Kepler 1625b. One team of scientists came out with some really compelling evidence for this huge, Neptune-sized moon. But then another team came along, used different methods to analyze the data, and argued that the signal just wasn't there. And that whole back and forth, it just shows you how ridiculously high the bar for confirmation really is. Okay, so if the clues are that subtle, what kind of tools are these cosmic detectives even using? Let's open up the Exomoon Hunter's toolkits. It pretty much all boils down to detecting the tiny, tiny effects, either visual or gravitational, that a moon has on its parent planet and its star. The number one tool in the kit is called the transit method. Here's how to think about it. Picture a really bright street light way off in the distance. When a planet crosses in front of its star, it's like a moth flying in front of that light. It just blocks a tiny little bit of the brightness, and we can measure that dip. Okay, now imagine a gnat flying around that moth. The exomoon, that's the gnat. It causes an even fainter, more complicated little dimming pattern, and scientists are trying to see that gnat's shadow from light years away. It's wild. Now, this is what's so cool. What you're looking at here is the actual forensic evidence. These are the light curves, the data showing the dips in starlight from that Kepler 1625b system we were talking about. See how the data points are kind of scattered? Scientists have to build a model that perfectly explains that dip. And the whole debate is about whether a model with just a planet is good enough, or if you need a model with a planet and a moon to really explain all those subtle little wiggles in the data. The second major tool is the radial velocity method. Now, a planet doesn't just circle its star like a toy on a string. They actually both orbit a shared center of mass. This means the star itself is making a tiny little circle in space, kind of wobbling back and forth from our point of view. An exomoon would add an even smaller, faster little wobble on top of that main one. And this is the perfect way to picture how we see that wobble. It's the Doppler effect. It's exactly like how the siren on an ambulance changes pitch as it comes towards you and then goes away. As the star wobbles away from us, its light gets stretched out into longer, redder wavelengths. And as it wobbles toward us, the light gets squeezed into shorter, bluer wavelengths. By measuring that tiny shift in color, we can feel the gravitational tug of a planet we can't even see. And maybe, just maybe, it's moon. So, if we've got the tools, why is this case still unsolved? Well, this is where we get into the complications.
The universe can be a pretty rough neighborhood, especially when a solar system is just getting started. And that makes forming and then keeping a moon a really serious challenge.
You have to realize early planetary systems are not these nice, orderly places we see today. They can be total chaos, with planets gravitationally knocking each other around in what scientists call planet-planet scattering. It's like a cosmic demolition derby. And as this simulation shows, those collisions can get so violent that a planet can get yeeted out of its system completely, becoming a lonely, rogue world drifting through deep space. So this leads to a really crucial question, right? If a planet itself can be treated like a cosmic billiard ball and get knocked right out of the pocket, what on earth happens to its moons? Well, they'd probably be stripped away or sent flying off into their own chaotic orbits. So the reason we find a planet all by itself today might be written in its violent past. And just to make things even more complicated, a lot of stars don't live alone. They exist in binary or even triple systems. In a setup like that, a planet and any potential moon can only have a stable orbit in these very specific zones. Either it has to orbit really tightly around just one of the stars, that's called an S-type orbit, or it has to orbit way, way out, circling the whole group. That's a P-type orbit. Any moon caught in between would get gravitationally booted out pretty quickly. Turns out the universe has some pretty strict rules about where you can and can't park a moon. Now, all this might seem like an awful lot of work just to find some space rocks, right? But there is a really powerful motive driving this whole investigation, and it gets right to the heart of one of the biggest questions we've ever asked. Are we alone? This quote from the research we're looking at today really says it all. The hunt for exomoons, at its core, is about expanding the search for life. We tend to focus on finding Earth-like planets, but habitable worlds could be hiding in plain sight, just orbiting big gas giants like our own Jupiter or Saturn. And here's why they could be such amazing candidates for life. A planet that orbits close to a small star would probably become tidally locked, meaning one side is forever baking in daylight and the other is permanently frozen in darkness. But a moon orbiting a gas giant in that same spot would be tidally locked to its planet, not the star. That means it would still spin relative to the star, creating a day-night cycle, and a much more stable, evenly heated climate, which sound like pretty perfect conditions for life to get started. So how would we actually look for life on a moon that's light years away? We'd use a really clever technique called transmission spectroscopy. As the moon passes in front of its star, a tiny, tiny fraction of that starlight has to pass through its atmosphere before it gets to us. And the chemicals in that atmosphere, things like water or methane or oxygen, they'll absorb very specific colors of light, leaving a unique chemical fingerprint for our telescopes to find. And this is what that chemical analysis looks like. It's a two-step process. On the left, you see scientists watching the transit over and over again, but in many different slices of color. For each color, they measure exactly how much the starlight dips. Then, when they plot the depth of that dip for every single color, they get the graph on the right. That is a transmission spectrum. And all those little peaks and valleys, those are the fingerprints of the chemicals in that world's air. So there we have it. We have the tools. We have a powerful motive. The investigation is still very much ongoing. And while we haven't cracked the case just yet, we know exactly what we're up against. This table really sums up the whole challenge perfectly. Every single method we have has its strengths, but also a major, major hurdle. The transit method, where we look for tiny variations in the transit's timing or duration, that's TDV and TDV, is fantastic, but the signal is just incredibly small. Radial velocity, you need a seriously massive moon to make a star wobble enough to see. Microlensing can spot distant moons, but the events are one and done. You can never go back and check your work. And trying to take a direct picture, it's almost impossible because of the blinding glare from the parent planet. It's truly a cosmic game of hide and seek on the hardest difficulty setting. But, and this is a big but, we're about to get a major upgrade to our detective toolkit. Amazing new telescopes like the James Webb Space Telescope are specifically designed with the kind of sensitivity we need to catch these super faint signals, especially those atmospheric fingerprints we just talked about. And down here on the ground, new radio telescopes like the upcoming Square Kilometer Array might be able to detect radio signals coming from the magnetic fields of these moons. Help is on the way. The cavalry is coming. So the case of the missing moons, it remains open. But I don't think it's going to be for long. The evidence is mounting that they have to be out there. The first confirmed discovery is coming, and when it does, it will open up a completely new chapter in how we explore the cosmos. It won't just be another new dot in the sky, it'll be a whole new type of world. And with that, a whole new universe of possibilities for where we might one day find life.